Let me begin with a word of prayer. I think everybody who's here is here. That much is safe to say. So, thank you for your quizzes. I'll begin. Dear Father, we thank you for this day. I thank you for the snow in places this morning, and thank you for these students. Just ask that you'd help us to use this time wisely, help us to glorify you in what we do, and help the students to ask good questions about math as they have them, Lord. In your name I pray, Lord Jesus. Amen. Now, let me get this out of the way. Sorry if you missed it, but have no fear. The attendance sheet is here. It's all that really matters. I'll probably give it to the grader, but she will use my solution to grade it, of course. And I think we should have the quiz back for you guys. I have an air horn in my possession. I can bring it to class if need be, but then you'll need to bring hearing protection as well, given the size of this room. Anyway, so yeah, the grader should grade the quiz over the weekend, and hopefully I'll have it back for you guys Tuesday, most likely. Yeah, that's the plan. And I should have the solution to the quiz posted before the end of business today, if all goes as planned. I was writing the solution right before class, and I made some stupid mistake, so I got to start again. Anyway. Okay, so you had a question, somebody had a question about the mission problem. Which one? Oh, so fun story. In my physics class, I get emails from a couple, and yeah, somebody told me yesterday in the email today, Dr. Cook, mission, module 4 is gone. Module 4 is gone. Poof. Module 4 in my Canvas for physics is just gone, gone. Except the thing is, it's not gone for me. For me, I see it. It's published. It's sitting there. But for some students, it's gone. So, Canvas is unreliable. All right? It just is. But the good news is, for you guys in here, hopefully I did this. I set up a course website, right? And so if you click on that, you notice that I've actually put your 3 required missions. If you ever have trouble in finding them in Canvas for whatever reason, they're here, right? And you just click on these links and save these PDFs, and then you've got all the required homework for the course. So, gentleman in the front, what would you like your name to be? Ethan, okay, I'll allow it. Ethan had a question about mission 1. So, let's go for it. What's your question?
Problem 18.
Problem 18. So I guess your question. So what was your question? How to do it? All right. Well, since you. Let's see here. So we're up against. So let me work a similar but possibly uglier problem. All right. So what I'll work for you is 13x squared, and I'll leave the other numbers the same. Okay. Because if we can solve 13x squared plus 3x minus 2, right? So let's find the solution, possibly complex, for that one, right? Now it may or may not actually have a complex solution. I don't know. Any other questions about the mission? Can I put it away? So now I guess now is as good a time as any to just, since I have it up here, which problems in the mission should you be able to do by now? Problem 1, you should be able to do that one. 2, problem 3, yep. Problem 4, 5, 6, yep. 8, 9, yep. We've covered 10, yep. 11. We've covered how to do all of these, certainly up through problem 14, and we're kind of currently, we just got done a couple lectures on problem 15 and 16, right? And 17. So 15, 16, 17, that's where lecture has been sort of processing the last hour and a half or so, right? Let's see here, graph each parabola. We talked about that last class, right? So problem 19 should be within your scope. 20 and 21 are kind of like last time. 22, we're talking about today. And 24 is, so like, you know, so pretty much up through problem 18 or so, you should be able to complete. I just wanted to put that, I wanted to mention that because I don't talk about this much, but there is a required homework, right? I haven't collected it yet. You need to be working on it. It's wonderful that you're asking a question about it today to remind me, to emphasize to you guys that there is a required homework and it is due when? Right, Valentine's Day, right? Is that the 14th? Yeah. So you show your love for math by completing your college algebra homework and turning it in all nice and pretty and stuff. Okay. Enough jibber jabber. How do we solve this? There are different choices. I gotta the zooming. Let's see here.
Mr. Cook.
What? I will not. My wife would not be happy about that. And there are other. I know it's surprising. I am married, but let's see here. So 13x squared plus 3x. What was that? All right. So what I'll do here is divide by. It just says to solve, right?
Over C.
Solve over C. So we could use the quadratic formula. Or we could try to complete the square and factor it. I think you guys need to see completing the square more than you need to see the quadratic formula. So let's complete the square here, see how it takes, see what happens to us. It's a little bit complicated because if I divide by 13, I get x squared plus 3 over 13x minus 2 over 13 equals to 0. Right? And, okay, so let's see here. What's half of 3/13? What's 1/2 of 3/13? 3/26. All right. So 3/26 is 1/2 of 3/13. I square it. So completing the square says I have to subtract 3/26 squared. A little bit ugly. And then I have subtracted 2/13 over here. Now, that's all equal to 0. I'm going to clean this up a bit. Isolate the square. So what I have is I have x plus 3 over 26 quantity squared is equal to 2/13 plus 3 over 26 squared. So what's that equal to? Something I said? Oh, sorry. I'll find a new joke eventually. See here. That's not true. I believe in recycling. Only for jokes, though. 3 divided by 26 quantity squared. That is apparently 113/676. Obviously, I used a calculator. But all that's going on there is making a common denominator of 26 squared. I think 26 squared is 676. Yep, 26 squared is 676. So you just make a common denominator of 26 squared. So like, you know, 2 times 26 plus 9 is that? Oh, I don't believe that. Oh, wait a minute, but I have to multiply this by 52. So 2 times 52 is 104 plus 9 is 113. Yeah, that makes sense. Now, this time, it wouldn't have mattered if the instructions had said, solve this quadratic equation over the reals. You would have still got the same answer. See, because whenever we complete the square and isolate the square, if we get equals to a positive number, that means the answer, there's a pair of real answers, right? If after you go through this and you rewrite it in this fashion and you've got a negative number over here, then that means you have complex solutions, right? Now, if we're talking about putting the number on the other side of the equation, the story reverses. But anyway, let me focus here. So we got x plus 3 over 26 is equal to plus or minus the square root of 113 over 676, which, by the way, you could rewrite as plus or minus the square root of 113 divided by 26. So the answer is x is equal to minus 3 plus or minus the square root of 113, all divided by 26, and there you go. So I think you can solve the one in the homework in this way. Alternatively, of course, you could just use the quadratic formula, right? Because this is what the quadratic formula would spit out. If you do minus b plus or minus b squared minus 4ac all divided by 2a, it gives you this. See, a is 13 here, so 2a is 26, and so forth, right? I recommend not using the quadratic formula to practice completing the square, because you need to practice completing the square, unless you're just like really good at it already. But anyway, other questions? Would you like me to work another? I mean, I can work another one of these, if there's interest. Otherwise, I will go on to the other material we need to cover. Bless you. Okay, any questions about anything then? Yeah. Yeah, what is the same kind of problem, or is there a particular other one you want to see? Or
No, just another one.
another one of these? Sure. I'll try to make this one turn out complex. Let's see what happens. So this was example 1. And this was a lot like problem 18 part C. Example 2. Let's see if we can solve, I don't know. How about 5x squared plus, let's say, 8x plus, I'll make it big, 100 equal to 0. Let's see if we can find the solution over the possibly complex solution, all right? So what I would do is I would first divide by 5 just to make things simpler, right? And in this case, that's nice, right? Well, it's mostly nice, but what happens? Well, this is a fraction. I guess we have to deal with that, right? What's 100 divided by 5? 20. All right. So again, I'm going to solve by completing the square and isolating the square. Okay, so like, here we go. This is x plus what? Squared. I want half of the coefficient of b. What's that here? What's 1/2 of 8/5? 4/5, right? So the arithmetic is a little bit friendlier than the last problem this time. And then to be fair, I have to subtract the square of that number. So I subtract 4 over 5 quantity squared, and I've still got my plus 20. So I'm going to isolate the square again because I'm just trying to solve this problem at the moment, all right? If I asked a different question, if I asked you to factor it, what I'm doing right now isn't what I would do, all right? But I'm just trying to solve it right now. That's the instructions. Solve this equation over C if possible. I mean, well, if I say over C, it's possible. Okay, so I got what? I've got minus 20 plus what is that? That's 16 over 25, right? Do you guys agree? 4/5 squared is 16/25. How does that, you make a common denominator, what are you going to do? No, I realized I haven't checked the audio. La la. Okay, we're good. Every so often, I forget to like turn on the mic, and then it's so sad. Actually, you guys are here. What do you care? But okay, so that's one thing to think about. If I'm going too fast in class, you can always go back to YouTube and put it to half speed, and watch me like talk much slower. I think there's even like, is there quarter speed in YouTube? I don't know. Yeah, no audio though. No, that's no fun. Let's see here. So if I turn to 25ths, I got what? What's 20 times 25? Yeah. So we got ourselves a 500, but that's a negative, plus 16 over 25. What's that? What? Minus, what's it? Yeah, minus 484 over 25, right? Okay, so if we take the square root of this, what do we get? X plus 4/5 is equal to plus or minus the square root of minus 484 over 25. Yeah? Which is what? That is, we have a negative square root, right? So we can factor, right? So yeah, plus or minus I over 5 square root of what? Oh, 484 is a square? Is 484 a square? It is? That's, you say it's 22 squared? Really? Ah, cool. I did not know that. So it's equal to plus or minus.
Sit back here as me.
So if you move up and sit next to her during the test, I'll have my eye on you. No, not you. You're not the problem. You're not the problem. Let's see. Let's see here. X is equal to. You got my back? Well, you're behind me, so 22i. So there you go. There's the solutions in this for this one. Now, listen, guys. I mean, I'm illustrating solving by the completing the square, but I will fully admit it might be a better course of action for you to use the quadratic formula on these. That's possible, right? If you were to use the quadratic formula on these to solve it, how would that look? I'll do it for this one. How would the quadratic formula solution go? Minus b plus or minus the square root of b squared minus 4ac divided by 2a, right? Which is what? Minus 8 plus or minus the square root of 8 squared minus 4 times 5 times 100, all divided by 10. And so, and then you just got to clean that up. Yeah, minus 8 plus or minus the square root of, yeah, 1936, I think. But there's a negative divided by 10. And then you have to clean that up, right? To get full credit, you have to clean it up. And it does simplify. And so minus 8 over 10 is, minus 4 over 5. And then plus or minus, let's say, I over 10, square root of 1936, which... It is a perfect square? 44 squared. You'll forgive me, but I must check. You are correct. So 44 squared, as everyone knows, 1936 is 44 squared. I mean, come on. Where you guys been? So minus 4 over 5 plus or minus I over 10 times, what do we say, 44? So what do we get? Minus 4 plus or minus 22i, all divided by 5. So we're right back to the same thing. It's just now most of the difficulty is just in simplifying the answer that the quadratic formula gives to you, right? I will say this, as a matter of custom, I usually do give partial credit if you have, at least got to here. I don't tend to give much partial credit for just this, because usually I don't feel right doing it, because students tend to make a lot of mistakes going from here to here, and if I just allow students to get credit for this, then I'm penalizing the people who did who did the work of trying to simplify the formula, which is an expectation of this course, you know. So anyway, let me stop blathering about my grading. Who cares? These are two different ways to do the same problem, yeah. However, what if I asked you to factor this quadratic? What would that look like? What if I say factor? And maybe not this one. Let's do example one. Factor 13x squared. What is it? 13x squared plus 3x minus 2. So what I would do then is I would factor the 13 out. And then basically the same that we did. And we know what that, we worked the arithmetic out there before. That works out to, what's the addition of those fractions was 113 over 676. So I get minus 113, 113 over 676. And then I have to look at it and go, oh, well, 113 over 676 is actually equal to the square root of 113 divided by quantity 26 squared. So really, if you look at it, it's the difference of squares, which means that I can factor that like so. And of course, another way you could look at this would just be to say, well, I know the answer. Yeah? Another way to look at this is to use what's called the factor theorem. If you know that the solutions to the quadratic equation are what we found before, then that means that you can rewrite the quadratic equation in terms of those answers. Like, let me just write it down. Factor theorem says this. It says this. It says f of c is equal to 0 means that x minus c is factor of f of x. We'll talk more about this. I don't want to talk about it too much today, but we'll talk more about that as we go on in here. This is the factor theorem. There's a correspondence, right? When you plug in the constant into the polynomial, you get 0. That means that there's a x minus c that's as a factor of the f of x. So like we have proved in example 1 that if I plug in, like this one, I'm putting c equal to, it's complicated, right? I mean, it's ugly looking. So here, my c was, minus 3 plus or minus the square root of 113 over 26. So example one, we argued that if you put c equal to that value, x equal to that value, minus 3 plus or minus the square root of 113 over 26, if you plug that in to this formula right here, you get 0. So the factor theorem says that if you look at the factorization of this polynomial, you must have x minus c as a factor. So like this is x minus that number. This is easier if let me not introduce this concept to you with like the most ugly possible example. Okay, so let me give us a much easier example to talk about this with.
It's always the most ugly example in our homework, so.
You say all the homework is ugly?
Yeah. Every time you do like a perfect problem on the board, when we do our homework, it's like.
Well, thank you. I don't think all the homework is whack, though. Let's see here. So, this was example 4. What? I think this is example 4. What's that? We'll say 4? Okay. So just to give you a simple example of the factor theorem, if I look at, say, f of x equals to, x squared, I'll keep it really simple, minus 3x plus 2. If we look at f of 1, what do we get? If we look at f of 2, what do we get? F of 1 is what? 1 squared minus 3 times 1 plus 2, right? Which is what? 0, yeah. What's f of 2? We've got 2 squared minus 3 times 2 plus 2. What's that? 4 plus 2 is 6. 6 minus 6, 0. So what does the factor theorem say? This says x minus 1 is factor. This tells me that x minus 2 is a factor. And of course, well, what is the deal here? Can you factor this? Well, yeah, right? X minus 1 times x minus 2 is indeed how that factors, right? But it's important to understand this interplay. A factorization of a polynomial tells you explicitly, just by looking at it, that there are certain numbers that if you plug in, you get 0, right? There's a correspondence between the factoring of the polynomial and the solutions to the corresponding equation, setting that polynomial equal to 0, right? They're not the same thing, right? Solving the equation is not the same as factoring. Are we good? Oh, so the one thing I left out of the discussion last time, which was domain and range. What's domain and range for a function? What's a function, by the way? Yeah.
A function is like you have an x and then you're trying to figure out the y.
You have an x and you're trying to figure out the y?
Well, like,
Okay.
so if you have like 2x and you give it like x is equal to 2,
Mm-hmm.
and then you do that.
I mean, I think that's kind of the right idea. I always introduce function as it's a machine, right? You feed it x and it spits out what? It spits out, y, which we call f of x, right? So, and for it to be a function, the rule has to be that you input 1x and you just get 1y out, all right? You don't feed a function one number and it gives you back 2, right? It has to be single valued. That's the rule. The domain of f of x, or the domain of the function, is all possible allowed inputs, and the range of f is all outputs which are attained, or you could say are reached, I don't know. And the other thing is, how do we look at functions? Well, we graph them, right? We graph functions. What's the graph of a function? That's y equals f of x, right? That's the graph of the function. And so if we graph the function, right, then the graph is a set of ordered pairs. And we usually draw some kind of picture, right? Like, for example, we could graph this example 5. Let's graph it. What's the graph of this parabola look like? Well, I know some things, right? I know that it goes through the x-axis. Where's it 0? 2 and 1, right? So at 1 and at 2, it's going through 0, right? Where's the vertex? I can complete the square. This is x minus 3/2 squared minus 9/4 plus 2, which is x minus 3/2 squared minus 1/4. So the vertex is manifestly at minus 3/2, which is 1.5, and minus 1/4, so it's kind of sort of about right here. Minus 3/2, minus a quarter. If you like it in terms of decimals, minus 1.5. Well, let me do it down here. Minus 1.5, minus 0.25. That's where the vertex is. I told you it's always halfway between the x-intercepts. Yeah? And what's the y-intercept for our graph right now? It's 2, right? So you've got x-intercept of 1, 2. You've got a y-intercept of 2. So it's like here. So I've got 4 points on my graph. Now I know what it looks like. It's a parabola, right? It's a parabola. And so here's the graph. So what's the domain and what's the range of this function? That's the thing I didn't talk about last time. All right? Can you guys tell me? Yeah, the domain of this function, it just goes on and on, all right? This is easy question. Anytime you have a parabola, the domain of the parabola is just all real numbers, okay? So that's kind of a boring question. The domain is minus infinity to infinity, all right? What's the range? So the range, so another way to say this is the x values are the input, the y values are the outputs, right? So to ask what the range is to ask which y values does the graph actually get to? -4 to infinity is correct. -1/4, right? I think that's what you said. Negative quarter all the way up to infinity. And there you have it. That's the domain and range. And that's always going to be the kind of story. Either you go to plus infinity or minus infinity, because the parabola either does what? It either goes up or it goes down. Which ones go down? The ones that the negative coefficient to the x squared term, right? Okay. So I need to talk to you guys about polynomials. What's a polynomial? An equation. Well, no, I would disagree. Well, I missed what you said second. It's you said with 3 or more parts. I mean, it doesn't have to be, but I mean that's kind of more the idea. So a polynomial is a function or an expression, we could say, right? It's an expression of the form something like this: an x to the n plus an minus 1 x to the n minus 1 plus dot 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 plus a2x squared plus a1x plus a0. So here the coefficients are numbers, and the numbers are in the one I just wrote above, a sub n minus 1, so forth and so on until I get to a2, a1, and a0. These are all real. These are all numbers, all right? And we assume, and if a sub n is not equal to 0, then the degree of f of x is equal to n. And it's understood that it's the highest non-zero coefficient defines the degree, all right? So like, let me just rattle off some really quick examples that'll just hopefully cement this idea. You guys tell me, what would be the degree of 3 minus 13x to the 100? What would the degree be of 3x squared plus 2x plus 11x cubed? Would that be? So how about the top one? What's the degree? The degree is 100, right? Because the highest term in there is this minus 13x to the 100. What's the degree of the next one? 3. Very good. What is the degree of ax squared plus bx plus c? So what is it? Trick question. I didn't tell you a was non-zero. Ha ha. I fell for it. No, it's complicated. So it's 2. If a is not equal to 0, it's 1 if A is equal to 0 but B is not equal to 0, right? And I think usually we would just say it's 0 if A and B are both equal to 0. So I usually say a constant polynomial is degree 0, a linear polynomial is degree 1, a quadratic polynomial is degree 2, right? But to be fussy, if you have A and B 0, it's still this pattern, right? It's just, anyway, so we usually, non-zero is important. Any questions? What happens if you multiply polynomials? So yeah, poly means many, and so it's many terms, right? We have special names, right? This kind of polynomial is called a cubic, right? This kind of polynomial is called quadratic. A linear polynomial is like this. If I have ax plus b, this is a linear polynomial, or degree 1. Our goal in factoring a polynomial is to factor it into a product of linear polynomials and quadratic polynomials, if we can. That's the goal. And why do we have that goal? Why do we care about factoring polynomials? I complained about something just a second ago. I asked her what a polynomial is, and the word equation was used. And that's not entirely wrong to think about equations, but is there an equation here? Don't mistake this for an equation. All this is a definition. I'm saying that f of x is this thing, right? But it's not an equation in the sense that an equation, you know, we have some kind of expression. We set it equal to 0 or equal to a number or equal to another expression, and then we ask what values of the variable make that equation true, right? For what x is that true? See, that question doesn't even really quite make sense, right? But if I set that equal to 0 and then I say, what x make that true? Well, that's a kind of interesting question, yeah? We already know how to answer that question for quadratics, right? If I give you a quadratic polynomial and I set it equal to 0, well, we can solve that, right? What about a cubic? So let's see here, example, oh man. Where was I? This feels like example 6. I feel like this was example 6. I could be wrong, but I may have skipped example. Maybe example 5 might not even exist. Oh, I think that's a 5 right there. Example 7. So suppose you have this. 2x minus 3 times, x plus 4 times x minus 1 equals to 0. What is the solutions to this equation? Can you tell me?
Would you have to boil it out first?
Oh no, don't do that. No. Think about this. If any one of those factors is 0, is the product of three numbers of which one of which is 0, 0? I mean, yeah, right? If one of those is 0, it makes the whole thing 0, right? So we don't need to multiplying it out. I mean, you can. We'll do it. Yeah.
Do you set each one equal to 0 and make them separate equations?
Exactly. Yeah. 2x minus 3 equal to 0, or x plus 4 equals to 0. There's 3 paths we can go down. Yeah. So the first factor is 0 when what? 3 halves, 1.5, I think you said. Cool. Or x is equal to minus 4, or x is equal to 1. And there you go. Those are the 3 solutions. So that's nice. And that's why we want to be able to factor cubic polynomials if we can. But can we? How do you do that, right? So I could multiply that out, but I'm going to resist the urge to do that because I don't think it would really serve any purpose to multiply that out here at the moment. And I think you guys can multiply polynomials out, right? Probably. I have some recommended homework to practice on from the R5 section. If you look at the recommended homework, R5, I've got 23, 25, 31, 33, 39, 41, 43, 49, 57, and 65. These are all just multiply out the polynomial. They're all odd, so you can check your answer in the back of the book and just check, make sure you know what you're doing there. Shouldn't take you long. Or maybe you already know. I can multiply polynomials. All right. So, example 8. Suppose we want to factor x cubed minus, I don't know, 4x squared. Well, just 4x, minus 4x, my bad. Can you factor this? How would you do it? X on the outside? X squared minus 4. So does everyone agree with that? If there's a common x across everything, we can pull x out, right? So that's one of our first lines of defense. Look for this. If you can do that, great. Oh, that is the difference of squares, right? Because we're looking at x times x plus 2 times x minus 2. And at this point, you know what we get to say? Done. Factored. All right? So factoring an expression is taking the expression you're given and rewriting it as a product of either linear or possibly quadratic factors, right? If we're factoring over R. So let me give you another example. Factor x to the 4th plus 6x squared plus, I don't know, 13x squared. Yeah. Factor what?
Yeah, so you put x squared out of the...
Pull the x. Now you want an x squared. You weren't content. You're not content with just an x. Now you want an x squared. But I'll allow it, right? Because that's the highest power of x that you can pull from everything here. And my bad. And this is, I'm only allowed to do this, but this was supposed to be a 3. Sorry about that.
Okay.
If that's not a 3, this is a easier and less interesting problem. It's like curses. All right, so yeah, I meant to put a cube there. All right, so once we put the cube there, what do we got? X squared plus 13. All right. X squared is done. Like, that's it. You can't further break that down. That is what it is. How about this quadratic? Can we factor that? You say, let me show you. So this is x squared times x plus 3, quantity squared, minus 9 plus 13, right? So lo and behold, this is x squared times x plus 3, quantity squared, plus 4, which shows me this is prime. And that's why we call it prime in the sense of factoring. Like, you can't break it down further. It's irreducible. You can't break it down, at least not without using complex numbers, all right? So we can play these games. There's another. Let's play another game here. Any question? No? Example 10. What if you're up against, I don't know, x to the 4th plus, let's say, 5x squared plus, I don't know, 4. Now your trick won't work. Well, you can't factor x out now, right? What? square root everything. Well, I can't just willy-nilly take the square root of stuff. It's not allowed.
But no solution?
You check your bank account and you're like, I had $1,000 this morning, and why do I only have like 30 now? And bank's just like, well, we just took the square root of your account. Like, you'd be annoyed, right? No, we can't just take square root.
No solution?
Do what?
No solution?
Well, we're not solving an equation. We're trying to factor. And I have some bad news. If the polynomial has degree larger than 2, it can be factored. Like the fundamental theorem of algebra says that any polynomial can be factored over the reals as a product of linear factors and prime factors, both of them possibly repeated. It's annoying, but it's true. Any polynomial of degree 3 or higher necessarily factors into something. Which is not to say that you can do it. All right? Like, it's possible to write down problems which are too mean for students to do. So was I any idea? Here, let me write a suggestive thing. So I once went to a math talk, and oh man, I'm jumping too far ahead. Too far. Sorry, my bad. Showing you too much. And he, on his slide, at the bottom of it, he said, "Warning, explicit material ahead." And I was like, it's awkward. And then he gets to the next slide, and it's just like this wall of equations. It was very explicit. I thought it was funny. I don't know. Let's see, really. Okay. So x squared squared plus 5x squared so you gotta free your mind, right? And look at this as maybe, I don't know, z squared plus 5z plus 4, where z is equal to x squared. So think about a substitution. Can you factor that? Yeah. See, that is z. So if I just like add 1 and add 4, that multiplies out, right? We factored it. And so going back, this is exactly x squared plus 1 times x squared plus 4. That's it. That's how you factor this polynomial. Now, there are problems like this in your recommended homework. If you look at like section, I think 3.3, number 107, 109, 111, these are like this, all right? So these are some of the recommended homework problems that I've recommended that you do parallel to this lecture, yeah? Any questions? Yeah?
Where did the z come
Oh, I made it up. I mean, you could make it Pac-Man squared plus 5 Pac-Man plus 4, where Pac-Man is equal to x squared if you want. It's just a letter. I mean, in fact, you don't even have to put it there at all. Like, once you see the pattern, you can just do it, you know? Like, for another example. Yeah, it's just a sort of training wheels, if you will, to make a step. Here, like this one. I won't do the I'll just do the thing this time. So like x to the 4th minus 11x squared. Oh man. Minus 12. So I do x squared, and I think about it and I go, well, plus 12, no, wait a minute, minus 12 plus 1, that should do it. So the idea is just to think about the x squared playing the role x did before. Are we done? Like, so, by the way, back here, you guys asked me a question, or I distracted myself. By the way, this was the answer. I can't go further than that, yeah? That's completely factored over the reals because both x squared plus 1 and x squared plus 4 are prime. You can't further factor these, right? These are prime. So over here, this guy, prime. We're done with that. Nothing more to do there. Nothing to see. The other one, though, x squared minus 12, that we can factor. How do you factor it? We do x plus the square root of 12, x minus the square root of 12, x squared plus 1, and there you go. That's how you factor this one. Now, there are a couple of other special forms I need to show you, but I would say, like, generically speaking, if I was just to pull out of my hat, you know, an arbitrary cubic polynomial and tell you to factor it, right? If I told you, you know, x cubed plus 3x squared minus x plus 7, and I said factor that, that's not a reasonable question. Why? Factor what I just wrote on the board. Why is that not a reasonable question? Can you factor that?
Would you have to split it into two?
Split it into two things. How would you do that? Take the first two and the second two. I mean, that's not a bad first attack, I would say. You're like, maybe you can use what's called factoring by grouping to make some kind of progress, but if I try that, that gives me x times x squared plus, or maybe x squared times x plus 3, right? And then I've got minus x plus 7, so it's like, yeah, all right. Oh well. Listen, all I'm trying to tell you is in the wild, cubic polynomials don't factor nicely. And the story of how they factor is really complicated. We have a quadratic formula I wrote on the board off memory. Not a big deal. You all probably know the formula too. Minus b plus or minus the square root of b squared minus 4ac all divided by 2a, right? Quadratic formula. Great. We know it. Some of us love it. The cubic formula. What is it? No one knows. That's not true. Mathematicians know. You can find it in textbooks. It's about a half a page. Even when there are real answers, there are cubic problems that have real answers as their equation. Like if you put the cubic equation equal to 0, even though the answer is real, the cubic formula involves complex numbers. It's weird like that. So it was one of the early proofs that we needed complex numbers to understand real equations. And so the story of the cubic equation is actually very interesting. You know, there was a couple mathematicians back in like the, I want to say 1500s, a fellow named Tartaglia, another one named Cardano, and basically they found the solution to the cubic equation. To make it really interesting, I really need to explain to you what completing the square means. Have you ever guys, do you know why it's called completing the square? This won't help you with your homework, but do you mind if I spend 5 minutes to show you? Maybe I shouldn't, but I'll tell you what, I'm not going to do it today, but it actually literally has to do with the geometry of completing a square. It means what it sounds like. You're taking and inventing this square corresponding to the equation, and the algorithmic process of completing the square corresponds to that geometric process of actually making a square from the equation. To solve the cubic, it corresponds to making a cube. So Cardano and Tartaglia, they understood this. And then, after much effort, another fellow, I forget if it was I forget who's who, but there's Tartaglia, Cardano, and then eventually Ferrari. These three people together found one of them is more important than the other. There's a wonderful video by there's a YouTuber who makes really good videos on this stuff. Veritasium, I think it is. And anyway, he has a wonderful 15-minute video on the history of the cubic and all this if you're interested. And long story short, we found up through the analog of the quadratic equation, through the quartic equation, there's even an equation for the arbitrary fourth order problem. The solution to that is like a page long, right? So my point to you is that while there are formulas known for cubic and quartic, they're so complicated that like no one writes them down, right? But then the thing that's even more annoying is past the fourth order, there is no quadratic equation. It's been proved impossible. You can't find a formula in terms of the coefficients, in terms of like a nice formula of coefficients for like a fifth order or higher in general. You're like, well then how do we factor? Well, we factor nice examples is the long and short of it, right? So there has to be some kind of nice pattern to be able to make the factoring reasonable. This one I don't think is reasonable. I just made it up off the top of my head, you know? So how do you find where it's 0? Well, you graph it. You use a numerical method. You use computers, generally speaking. And there's a simple approach, like if you can find where it's positive on one side and negative on the other, then because the graph like is continuous, you know it's 0 somewhere in between. So like that's basically the idea. You can then approximate where the 0 is. All right, let's get back to graphing. I mean factoring, my bad. So there are some patterns though which are nicer. So here's one. So this is nasty, but this one I can factor. And this one I can factor. Let me tell you how. So here's the deal. A cubed minus b cubed is a minus a b times a squared plus ab plus b squared, I believe. Now, you may doubt me. I doubt me. I multiply it out to check, okay? So if you multiply this out, you get a times a squared, which is a cubed. This gives us a minus ba squared. This gives me a plus ba squared. Those cancel. We also have a, let's see here, how'd it go? A squared b and minus ba squared. Good. So there you go. This is an identity. This is one of the special form trinomials. All right. There are like a couple formulas like this. They're both, I think, in your section 3.3. I'm writing them down for you right now. So that's one of them. Oh man, I thought it was here. I should have put a sticky note. Rats. Oh well. Anyway, this is true. So that's one thing. There's also a sum of cubes. If I have a cubed plus b cubed, what's that look like? I believe that is the sum of cubes formula. I think I let you guys have a index card or a sheet of notes or something for the test, don't I? This is one of those things I put on there because I don't want to try to remember it off the top of my head. And like, why does that help you? Well, it doesn't help you with example 13, does it? Not really. But example 14, can we apply it there? This is what? A cubed minus b cubed, isn't it? Where what's b? B is equal to 3. If we take the cube root of 27, it's 3. So that's really, you know, x cubed minus 3 cubed. And then according to the difference of cubes formula, we get x minus 3 times x squared plus ab, which is plus 3x here, and then plus 3 squared, which is 9. And there you go. That's it, guys, for the factoring of that. You might be like, wait. How do you know the quadratic is prime? Why, I know.